menciptakan dan membentuk SDM yang kompeten, profesional, dan berdaya saing tinggi. PPSDM fasilitasi seluruh peserta didik dengan sarana dan prasarana yang sudah memiliki standar ISO. Laboratorium dan workshop menjadi fokus sarana dan prasarana di wilayah Pusdikat KEBTK.
PPSDM KEBTK, Kementerian Energi dan Sumber Daya Mineral, telah bertransformasi menjadi sebuah lembaga pengembangan SDM di bidang ketenagalistrikan dan EBTKE yang unggul dan selalu menjaga kualitas layanannya. PPSDM KEBTKE mendukung target nasional Net Zero Emission 2060 melalui transisi energi yang harus diwujudkan oleh semua pihak untuk mengurangi dampak perubahan iklim bagi kehidupan masyarakat. Selain itu, Indonesia memiliki energi baru terbarukan dengan potensi yang tinggi, mulai dari matahari, hidro atau air, angin, bioenergi, panas bumi, serta lautan. Hal inilah yang membuat kami semakin matang dan siap melayani Anda. Kami didukung oleh para fasilitator yang berkompeten dan fasilitas yang lengkap sesuai dengan kebutuhan pelatihan, sertifikasi, bimbingan teknis, dan layanan penunjang lainnya. Pelatihan dan sertifikasi dilaksanakan dengan layanan yang prima. Bergabunglah bersama PPSDM KEBTKE.
Baik, izin untuk memulai. Assalamualaikum warahmatullahi wabarakatuh. Salam sejahtera untuk kita semua. Om Swastiastu, Namo Buddhaya, dan salam kebajikan. Yang kami hormati Kepala Pusat Pengembangan Sumber Daya Manusia Ketenagalistrikan, Energi Baru Terbarukan, dan Konservasi Energi, Bapak Insinyur A. Susatyo Edi Prabowo, MSI, para pejabat pimpinan tinggi Pratama di lingkungan Kementerian SDM, narasumber Bapak Robert Haberl dari Eastern Switzerland University of Applied Sciences, OST, para peserta webinar, selamat siang Bapak dan Ibu, Mas dan Mbak, Sobat Energi yang saya hormati dan banggakan. Perkenalkan, nama saya Dian Elvira Rosa, MC sekaligus moderator pada acara siang hari ini. Pada tanggal 17 Juli ini, Pusat Pengembangan Sumber Daya Manusia Ketenagalistrikan, Energi Baru Terbarukan, dan Konservasi Energi, PPSDM KEBTKE, menyelenggarakan webinar dengan mengangkat tema Optimizing Thermal Energy Storage for Smart Systems and Heat Pumps. Webinar ini diselenggarakan oleh PPSDM KEBTKE bekerja sama dengan pemerintah Swiss, State Secretariat for Economic Affairs (SECO) melalui proyek Renewable Energy Skills Development sebagai bagian dari tugas dan fungsi PPSDM KEBTKE dalam mengembangkan sumber daya manusia di bidang ketenagalistrikan, energi baru terbarukan, dan konservasi energi, serta sebagai sarana diskusi terkait isu-isu terkini di sektor SDM KEBTKE. Bapak, Ibu hadirin yang kami hormati, saatnya kita dengarkan sambutan Kepala Badan Pengembangan Sumber Daya Manusia, Energi, dan Sumber Daya Mineral yang akan diwakili oleh Kepala PPSDM KEBTKE yang sekaligus akan membuka webinar siang ini. Kepada Bapak Insinyur Susatyo Edi Prabowo, MSI, waktu dan tempat kami persilahkan.
Terima kasih, Bu Dian. Yang saya hormati Mr. Robert Haberl dari Institute for Solar Technology Eastern Switzerland, University of Applied Sciences, selaku narasumber. Thank you, Mr. Robert Haberl. Yang saya hormati Bapak Ibu panelis yang terdiri dari pejabat pimpinan tinggi Pratama, pejabat administrasi dan fungsional di lingkungan Kementerian ESDM beserta undangan. Yang saya hormati para peserta webinar ketiga tahun 2024 PPSDM KEBTKE yang mengikuti kegiatan ini baik melalui akun Zoom, YouTube, dan sosial media PPSDM KEBTKE yang berbahagia. Assalamualaikum warahmatullahi wabarakatuh. Selamat siang dan salam sejahtera bagi kita semua. Puji dan syukur kehadirat Allah Subhanahu wa Ta'ala, Tuhan yang Maha Esa, atas berkah dan karunia-Nya kita dapat berkumpul hari ini, Rabu 17 Juli 2024 dalam keadaan sehat walafiat, untuk mengikuti webinar yang sangat penting ini guna menambah wawasan dan pengetahuan serta informasi terkait ketenaga listrikan, energi baru terbarukan, dan konservasi energi. Para panelis dan peserta yang kami hormati, alhamdulillah kita patut bersyukur bersama bahwa kita dapat dipertemukan kembali dalam acara webinar PPSDM KIPTKE yang ketiga di tahun 2024 ini, dengan mengangkat topik Optimizing Thermal Energy Storage for Smart Systems and Heat Pumps, yang akan disampaikan oleh Mr. Robert Heber dari Institute for Solar Technology, Eastern Switzerland University of Applied Sciences. Seperti kita ketahui bersama, energi adalah salah satu pilar utama dalam pembangunan berkelanjutan. Di tengah tantangan global terkait perubahan iklim dan kebutuhan energi yang terus meningkat, kita dituntut untuk menemukan solusi inovatif yang dapat mengoptimalkan penggunaan energi secara lebih efisien dan berkelanjutan. Salah satu solusi yang menjanjikan adalah teknologi penyimpanan energi termal yang memiliki potensi besar untuk mendukung smart system dan heat pumps. Penyimpanan energi termal adalah teknologi yang memungkinkan kita untuk menyimpan energi dalam bentuk panas maupun dingin dan menggunakannya sesuai dengan kebutuhan. Teknologi ini sangat relevan dalam konteks smart system dan heat pumps, di mana efisiensi dan pengelolaan energi yang optimal menjadi kunci utama. Dengan mengoptimalkan penyimpanan energi termal, kita dapat mengurangi beban puncak energi, meningkatkan efisiensi sistem, dan mengurangi emisi gas rumah kaca. Sistem cerdas atau smart systems memungkinkan integrasi yang lebih baik antara berbagai komponen energi, termasuk sumber energi terbarukan, penyimpanan energi, dan penggunaan akhir energi. Dalam ekosistem ini, penyimpanan energi termal berperan sebagai jembatan yang memungkinkan keseimbangan antara pasokan dan permintaan energi. Bapak, Ibu, panelis, dan peserta yang kami hormati, optimalisasi penyimpanan energi termal untuk smart system dan heat pumps tidak hanya memberikan manfaat ekonomi, namun juga memiliki dampak positif yang signifikan terhadap lingkungan. Dengan meningkatkan efisiensi energi dan mengurangi emisi, kita turut berkontribusi dalam upaya global untuk mengatasi perubahan iklim dan melestarikan bumi untuk generasi mendatang. Pada webinar kali ini, Badan Pengembangan Sumber Daya Manusia Kementerian ESDM melalui PPSDM KIPTKE mengundang ahli dari Institute for Solar Technology untuk memberikan materi terkait thermal energy storage. Adapun topik yang akan dibahas mencakup pengenalan thermal energy storage, efisiensi thermal energy storage, implementasi pada sistem smart dan energi terbarukan, serta perkembangan thermal energy storage di Indonesia. Melalui pemaparan dan diskusi, diharapkan webinar kali ini dapat mendukung proses transisi energi Indonesia yang berkeadilan, serta dapat mencapai target net zero emission paling lambat pada tahun 2060 atau lebih cepat. Marilah kita manfaatkan acara ini sebagai platform untuk berbagi pengetahuan, pengalaman, dan inovasi. Dengan kolaborasi dan komitmen bersama, saya yakin kita dapat mencapai terobosan-terobosan baru yang akan membawa manfaat besar bagi masyarakat dan lingkungan. Bapak, Ibu, para panelis, dan peserta yang kami hormati, sebagai penutup, marilah kita panjatkan doa, semoga kegiatan webinar ini terselenggara dengan baik. Tidak lupa, pada kesempatan ini saya menyampaikan ucapan terima kasih kepada pemerintah Swiss melalui Renewable Energy Skills Development Project dan Institute for Solar Technology atas dukungannya dalam penyelenggaraan webinar kali ini. Terima kasih juga kepada narasumber, panelis, moderator, dan peserta webinar. Semoga Allah Subhanahu wa Ta'ala, Tuhan yang Maha Kuasa, senantiasa memberikan petunjuk dan merahmati setiap langkah dan upaya kita bersama. Akhirnya dengan mengucapkan Bismillahirrohmanirrohim, kegiatan webinar PPSDM BTKE yang ketiga di tahun 2024 ini saya nyatakan dibuka secara resmi. Sekian dan terima kasih. Wassalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh. Terima kasih banyak Pak Edi atas kata sambutannya yang telah mewakili Bapak Kepala BPSDM SDM dalam membuka secara resmi webinar pada hari ini. Sobat Energi, sebelum kita memasuki acara utama pada siang hari ini, saya ingin mengumumkan 3 hal. Yang pertama, paparan dari narasumber serta sesi diskusi akan dilakukan dalam bahasa Inggris. Namun, kami telah menyediakan penerjemahan simultan bagi Bapak Ibu yang ingin mendengarkan dalam bahasa Indonesia. Caranya gampang sekali, tinggal klik icon atau gambar bola dunia di bagian bawah layar Zoom masing-masing dan pilih opsi bahasa Indonesia. Yang kedua, akan ada hadiah menarik dari RSD berupa voucher e-money untuk 2 penanya terbaik yang akan diumumkan di akhir acara. Jadi Bapak Ibu, selama sesi paparan, apabila memiliki pertanyaan, langsung saja tulis di chat box dan pertanyaan-pertanyaan terbaik akan dipilih oleh panitia serta dibahas dalam sesi diskusi nanti. Pertanyaan bisa dalam bahasa Inggris maupun bahasa Indonesia. Lalu yang ketiga, sertifikat elektronik akan diberikan bagi peserta yang menghadiri acara sampai selesai dan mengisi formulir evaluasi. Link formulir evaluasi dan cara untuk download sertifikatnya akan diumumkan di chat box di akhir webinar ini. Baiklah Bapak Ibu, memasuki inti dari acara yaitu paparan dari narasumber. Telah hadir bersama kita Bapak Robert Haberl, peneliti senior dan project manager dari Institut Teknologi Surya (SPF) yang merupakan institut penelitian terbesar di Eastern Switzerland University of Applied Sciences (OST). Welcome, Robert. It's a pleasure to have you with us, and we're very much looking forward to your presentation and discussion later. Bapak Robert adalah figur terkemuka di bidang sistem energi, dan beliau telah berkarir lebih dari 10 tahun di Institut Teknologi Surya sebagai peneliti dan manajer proyek skala nasional dan internasional. Keahlian beliau adalah simulasi dan pengujian perangkat keras dalam putaran atau hardware in the loop test, khususnya terkait penyimpanan energi. Bapak Robert turut berperan dalam pengembangan metode pengukuran efisiensi stratifikasi tangki penyimpanan. Latar belakang pendidikan beliau adalah diploma teknik mesin dengan spesialisasi teknologi energi dari Universitas Ilmu Terapan di Ulm. Mari kita beri sambutan yang meriah bagi Bapak Robert. And Robert, you can share your screen directly if you wish and operate your PowerPoint. The time is yours. Thank you.
Thank you very much. I would like to thank you for having me here and allowing me to talk about the topic of solar energy storage and optimizing solar energy storage for smart systems. I share my screen and then you should see my presentation. So.
Yeah, okay. We can see it now.
Thank you very much. So, optimizing thermal energy storages for smart systems and heat pumps is the topic of today. And I would like to talk about give you a brief introduction about our institute, then why we should store heat, why is water efficient to store heat, what is a stratification of storage tanks and why is this important, and then I give you information about what processes destroy stratification and how could it be prevented, and some bad and good examples of storage tanks. Okay, in the beginning, I would like to raise some questions. Maybe you can answer during the presentation in the chat, and I will come back to those questions in the end of the presentation. And the questions are: what physical properties of water make it a good choice for storing energy? And the second question is: what is the biggest problem when combining heat pumps with water storage tanks, and how is it solved? And the third question is: what has a greater influence on the performance of the overall system, the energy losses or the exergy losses of water storage tanks? So you can keep those questions in mind, maybe answer already now, and we will come back to it in the end. I will start now with a brief introduction about the OST, that's the Eastern Switzerland University of Applied Sciences. It's an university with 3 different locations in Bux, Rapperswil, and St. Gallen, which is capital of a region in Switzerland. We have 6 different departments, 22 different studies, and we have over 180 corporations with different international partners. We at SPF are the biggest institute on the university. We have 50 employees, 35 of them are in research and development. And we are 95% third-party funded and have 2.5 full-time positions via teaching. The rest is in research projects active. So where we come from is solar thermal energy, meaning solar collectors to generate heat from sunlight. And we started with that in the year 1981. And if you deal with solar thermal energy, it's also crucial to deal about energy storage, because the sun is shining on a time when we probably don't have any heat demand, but we would like to collect it and store it for later use. The solar energy systems and energy storage was from the beginning part of our focus in the institute. In the meantime, we expanded, we widened our view. We added things like district heating, solar process heat for industries, higher temperature heat demand for industries, energy efficient building technology, and of course also photovoltaics, which is now also a big part in our daily business. And we are in the whole chain with product development, simulations, testing of different components. You mentioned in the introduction the hardware and the loop tests, where we test the interaction of components like heat pumps with storage tanks and PV cells. And we also work in the development of those components. So that's our introduction. Now I would like to go to the topic of today's presentation with the question, why store heat? What is the reason for storing heat? But why is it necessary? So there are several reasons. First is a load balancing, meaning you can decouple the production of heat and the consumption of heat, which is especially true when you have fluctuating renewable energies that should be stored. But it's also true if you have a heat generator that is in power not big enough to cover the peak demands, which is the second reason for storing heat. Sometimes you have a demand that is higher than your generator capacity, and then you can use a generator to store it in a tank and release it in a short time when needed. The third reason is energy efficiency. It can improve the energy efficiency by capturing and storing excess heat that would otherwise be wasted, and you can use it then later when it is needed. The next reason is cost savings. By storing heat, you can take advantage of off-peak electricity, especially when you combine it with heat pumps. Then you can use the heat pump to generate from the electric energy, thermal energy, and store it for later use when the tariffs are low, or when you have an excess in heat or in electricity. That is also true, or the reason is the renewable energy integration. We talked about it. Renewable energies are fluctuating, and you need to have some kind of buffer between the demand and the production. And with all those measures, you can reduce the carbon emissions by improving energy efficiency and facilitating the use of renewable energy. Heat storage can help reduce carbon emissions and combat climate change. The reason of seasonal storage is true in countries like Switzerland, where we have a big heat demand in winter and lot of sun in summer. And then we can shift the energy to winter, but it's not a crucial point for Indonesia, I understand. But industrial processes, many of them produce waste heat, and there are lots of processes that needs heat in a temperature range that could be provided by renewable energies. And for that case, also in industrial processes, storing heat is a technology that is important. So that's a picture from Switzerland. That's the final energy consumption. As you see, around 1/3 of the energy consumption is electricity, and part of that electricity is also used to generate heat via heat pumps in residential buildings and also in offices or other buildings. Then we have around 1/3 of fuels for mobility, and the rest of the demand is oil burning some combustibles that is used to generate heat, meaning that part is a demand for heat. Half of the electricity is heat. So in Switzerland, half of the energy demand is heat. In winter times, it's more. In summer times, it's less. But roughly half of the energy demand is heat. If we have a look on the energy consumption, the final energy consumption in Indonesia, we have lower share of electricity, but we also have again around 1/3 of fuel for mobility, and LPG is, as I think, also used for mobility. Maybe you can correct me if I'm wrong. The rest of the energy demand is also always combustibles like coal, blending products of biogas oil, gas oil, natural gas, biogas, and all of them are kind of storage. It's chemical storage of energy, and it's released via combustion and producing heat. And that heat should be used later in different temperature ranges. And the use of coal and other things that we burn should be replaced by heat that is generated from renewable resources, maybe from solar thermal, maybe from PV in combination with heat pumps. And that part is also a part where the heat storage could be applied. If you look on the energy consumption by sectors, you have the industrial sector as the biggest part. That means in industrial sectors, the storage of heat is a part where the impact is the biggest one. And here, the heat demand that is lower than, let's say, 200 degrees is the first to tackle. In food industry or other industries, there is a high energy demand that could be used with waste heat or other sources where the storage could be applied. In households, it's a lower share, and in households, the energy storage could be used or has to be used for domestic hot water. And also cooling is a part where the energy storage could be used for having a higher energy efficiency overall. So we see a demand for storing heat, and we have different technologies. I would like to talk about why water is efficient for storing heat. But before I do so, I would like to give you a brief overview about the types of thermal energy stores. We have three main types. First is the sensible heat, meaning storing heat that changes their perceptible temperature during the charging or discharging process. This does not undergo a phase change or a chemical reaction. It's storing heat in a medium that does not change. The second one is latent heat storage. These do not change their perceptible temperature during the charging or discharging process, but the heat storage medium changes its state of aggregation. This is usually the transition from solid to liquid or vice versa. I come back to that later on. And the third is the thermal chemical heat storage or sorption storage. These store heat using endo or exothermic reactions with, for example, silica gel or zeolites. And depending on the temperature range, these storages can be further classified as low temperature storage. That's store of heat up to a temperature of 100 degrees Celsius. That's a typical range for sensible heat with water as a medium in residential buildings for domestic hot water storage. Then we have a medium temperature storage that's up to 500 degrees. That could also be done with sensible heat with water storage tanks. If they are pressurized, you can go up to 180 or maybe 200 degrees Celsius with a water storage tank. And the third is high temperature storages. Then that can store temperatures over 500 degrees Celsius. And here, water is not the right solution. If you use sensible heat storages, you could use molten salt, for example, or a new technology is molten aluminum. But that's not the focus of my today's presentation. So we see different types of storages and different temperature ranges. But why is it efficient to use water as a storage? First is we have a high specific heat of the heat capacity. Water has a high specific heat capacity of about 4.18 kilojoule per kilogram in Kelvin, which means it can store a large amount of heat per unit mass. If you compare it with the other materials I had in this place, it's obvious that water is a good solution. I mentioned the salt, the molten salt before. That has around 1.5 kilojoule or 1,500 joule per kilogram in Kelvin, and water is has a very high capacity compared to that. But there are other reasons, like the availability of and cost. Water is readily available and inexpensive, making a cost-effective choice for thermal energy storage. Safety and environmental impacts. Water is non-toxic, non-flammable, and environmentally friendly. It does not pose a risk of chemical spills or fires. That's also important. It's compatible with infrastructure. Many heating and cooling systems are designed to work with water. So using water as a thermal storage medium can simplify the design and integration of the storage system. And then we have the phase change. Water has a high latent heat of fusion. That means not only the specific heat capacity is important, but also the heat of fusion, meaning it can store or release a large amount of energy during the phase change from solid to liquid. The enthalpy of fusion is 334 kilojoule per kilogram. This property is exploited in systems like ice storage tanks. But there is another physical property that is very important, at least for the sensible heat storages, and that is the density. I come back to that later, but the density allows a stratification inside a water tank. You see that the density is lower with rising temperatures. It's 960 kilogram per cubic meter at 100 degrees Celsius and close to 1,000 kilogram per cubic meter at around 4 degrees Celsius. And that allows water, like you see here in an ocean, in a water basin, that the warmer temperature is in the top range, and then we can see big drop in temperature. If you see here the decrease in temperature over a small distance, and then it keeps stable down to the ground of the ocean. And we can use this physical property for the stratification of storage tanks, where I come back later on. So water can be stored in simple tanks. You can build huge tanks. You see here a non-pressurized storage tank for district heating. That is in the temperature range up to 100 degrees. Same temperature range here in a small domestic hot water storage tank that is maybe 200 liters for hot water storage. But in industry, you can have also these pressurized storage tanks with temperatures up to 180 degrees Celsius. And you can simply put water in, hot water in or out, and connect it to the rest of your system, which makes it easy. That's for sensible heat storage. But you can also use ice storages for the use in solar ice systems. They make use of the high latent heat released during phase change. You see here a system with a heat pump that is providing heat for later use. And during that production of heat, it needs to have a source on the cold side, the source side of the heat pump. And you can use water as source at the temperature of 0 degrees, where it releases large amount of energy in the phase change. And that ice could be stored in an ice storage. And that ice storage again is a part that could be used for cooling demand. So you can produce both heat and cold with a heat pump, use the heating for domestic hot water, and the cooling for producing ice in an ice storage tank. The state of the art on ice is a so-called ice on coil. That means you have a large installation where you have this heat exchanger inside a big water tank, and you extract heat from that water reservoir during usage of the heat pump, and you build up ice that is on that heat exchanger growing. You have also disadvantages with that technology because the heat exchanger is crucial and you can't scale it. You have a cost scales with kilowatt hours, not with kilowatt. That meaning a bigger storage tank needs more investment cost. But there are also different types of ice. The ice slurry storages are also a technology. Ice slurry means you have not a solid ice, but you have like a pipe with a solid part, but it's pumpable. It behaves like a liquid. Here, the state of the art is a so-called scraper. You have a heat exchanger on the wall of that tank, and you build ice and you scrape it down to have these small particles then on the bottom, and then you can use that ice for different applications. But there is also another technology available to produce ice. That is the ice slurry generation. That's again with a heat pump. You have a heat pump and you extract heat on that supercooler, and you extract heat of water of 0 degree, and you supercool it down to -2 degrees. If you do it with pure water, you can do it without building ice, but you already use the energy of fusion by supercooling it. And then you need a crystallizer that starts the crystallization of the water to ice, and you can store the water ice mixture then in a simple tank. So the ice slurry storages use a heat exchanger that has to be coated with an isophobic coating. With that heat exchanger, you supercool the water and you bring it to a crystallizer that starts the nucleation of ice cores. And then you could put this ice in a tank and use that ice later for different cooling applications. We tested that in our lab, and we have several projects. Maybe when you want to have a look on those projects, you can follow those links, where different ice slurry projects are done, which is, I think, an interesting technology for Indonesia because of the cooling demand. So, but the focus is again back to the sensible heat storages with the stratification. I mentioned before that the stratification is a natural process that has its origin in the decreasing density of water when the temperature rises above 4 degrees Celsius. So you see here 3 different energy storages. The energy content is the same for all temperature profiles. With the pronounced stratification, the less pronounced stratification, or the no stratification, or the completely mixed tank. The average temperature is always the middle temperature. The exergy content varies, so meaning the useful energy related to the temperature where it should be used. And the exergy content is highest with the good stratification, and then lower with the less pronounced stratification, and there we have no exergy storage at all because it's not useful if it's fully mixed. A temperature sensor in the upper storage area registers hot for perfect stratification, but only lukewarm in the unstratified case. So how does this look in a storage tank? There we have stratified versus a non-stratified storage charging with solar thermal collectors. You see here a storage tank with temperature sensors on the wall of the storage tank. You see this in the graphic beside. In the first case, you have an immersed heat exchanger, non-stratified. That means you put in the heat on the lower part of the storage tank. And you see the temperature increases simultaneously on the different heights of the storage tank, meaning the collector return temperature also rises, and that means the efficiency of the solar collectors decreases. It's the same for a heat pump. If you want to heat it with a heat pump and the return temperature or the lower temperature increases, the efficiency will drop. In the next case, you also, again, have the immersed heat exchanger, but that time you have a stratification lens, meaning the water is captured and forced to rise in that lens, and it can escape on the holes on the side, on the part where the density of the water is the same as the density of the heated water. And here you have a temperature increase with a time lag, meaning it rises on the top of the storage tank first, then in the second position and the third position, and only last on the bottom. And that allows the return temperature to keep low a long time. That allows to heat the storage tank to a useful temperature quite early, and increases therefore the exergy content of the storage tank and the efficiency of the overall system. And why is this important? So there are several reasons for that, why this is important. The first is the utilization of volume. Again, a fully mixed storage tank, 10 cubic meter, mean temperature 40 degrees Celsius. You put in 5,000 liters of 60-degree hot water, and you get a tank that has higher part with 60 degree and a lower part with still 40 degree. So after that, already 5,000 liters can be supplied at a level of 60 degrees Celsius. But if you have a mixed charging, the tank is now 50 degrees Celsius. It has the same energy content, but not the same exergy, because the temperature is not useful. If you have a process that needs 60 degrees Celsius, you can't use the 50. So you have to wait until you have the whole storage tank at the correct temperature, and only then can you use the heat. The volume part is the first reason. The second reason is the efficiency. I talked about solar thermal collectors that are more efficient if the temperature is low, but the same applies for the COP of a heat pump. It gets better when the sink temperatures are lower and the source temperature are higher. The 1 Kelvin higher sink temperature means a 2 or 3% lower COP of the heat pump. That means with every Kelvin, the lower part of the temperature of the storage tank rises, the efficiency drops, and therefore you have to avoid exergy losses and mixing processes and heat transfer processes inside the storage tanks. You can see in the next slide the results of good stratification with domestic hot water tanks, which is also important for Indonesia. A project where we measured different storage tanks and we measured the stratification efficiency and we calculated we measured the energy, that is the electric energy that was used to heat the storage tank. With a good stratification, we reached a performance factor of the heat pump of almost 3. And with a poor stratification, it was only 1.5. And you see the big difference is the average temperature of charging. The average temperature of charging is lower with a good stratification efficiency. That means for the same temperature that is delivered and the same energy content that is delivered, you can put in average a lower temperature with a good stratified storage tank and have a big difference in the efficiency of the storage tank. Another reason for good stratification is the topic of Legionella. You see the temperature regions where Legionella reproduce. They hardly reproduce with a temperature lower than 20 degrees. There is a slow growth already at 25 degrees, increase up to 45 degrees Celsius with an optimum at 37 degrees Celsius. And you can deactivate them above 50 degrees Celsius, and you can kill the Legionella when you are above 60 degrees Celsius. Now, if you have a storage tank with a temperature distribution like that, with a very good pronounced stratification, meaning the lower part sets the height of the thermal storage tank, sets the temperature. If the lower part is cold, and you have very rapid rise in temperature over a small region and a hot part in the end, you have a growth area for Legionella that is very small and that moves with charging and discharging of the storage tank, reducing the time where the regions of the storage tank are in a critical phase. If you have a not as good stratification, the growth area is big, and the growing of Legionella is in a bigger part of your storage tank. So we saw that stratification is important, but the next question is which processes disturb or destroy the stratification? And there are 3 effects to be mentioned. That picture is showing a storage tank again. The colors represent the temperature in the storage tank, and that is the storage wall. We have here heat conduction in the wall of the storage tank, in the water itself, and also in the parts in the tank like heat exchangers or other parts. And that means it's a heat transfer and production of entropy or loss of exergy. To avoid that, you can build tall and slim storage tanks. The second is the entraining current or the plume entrainment, meaning you bring in the heat in a part of the storage tank where it's not the same temperature as in the surroundings. Then the water has to find its way on its own to the correct position, and on that way it will transport some more water to the wrong position and lead to mixing. Therefore, you should insert the medium at the correct height. If necessary, you can work with a stratification lens, as we saw before. For solar heat, you put it usually in the lower part of the storage tank. And to avoid this plume entrainment mixing, you can use a stratification lens. And the third and most important is this that is shown here, that the turbulent inflow with a high momentum, and it's called the inlet jet mixing. That is especially true with heat pumps, because heat pumps work with a low delta T and high flow rates, meaning you have only 5 Kelvin between return and supply, but you are very quickly at like 2 cubic meter with a 10 kilowatt heat pump per 2 cubic meter per hour. And that inlet jet mixing destroys the stratification in the storage tank. So first, tall and slim storage tanks to avoid the heat conduction. Use stratification lenses or the correct position of inlet to avoid the plume entrainment. And the third is calming down the fluid to a velocity below 0.1 meter per second. There are different measures to do that, and I will show you some bad and good examples for that slowing down the speed of the fluid. Here you see a CFD simulation of a storage tank that has in the beginning a good stratification, 50 degree at top and 30 degree in the lower part. And you have an inlet in the middle of the storage tank. And you see here what the way of the fluid is. It's set fast that it goes all the way through the tank to the other side of the storage volume. And there it is distributed all over the storage tank, and then you reduce your temperature profile in a short period of time and mix the hot water down to a lower temperature. If you have only 900 liter per hour, you have significantly less disturbance of the upper zone. The incoming fluid has a much lower velocity and has already been strongly deflected downwards when it hits the opposite storage wall, so that the resulting deflection also takes place mainly downwards, and you keep the upper part hot while charging the lower part to a lower temperature. There are different methods to slow down the speed of the fluid, and it's also important that after you have a flow in a change in direction, you have to calm down the fluid, meaning you have to have a diameter of a pipe that is big enough to have a low velocity below 0.1 meter per second, but the length of that pipe is also important. You see here the pipe feed to the storage tank, then it divides into 2 branches, and the length varies in different CFD simulations. And you have the distribution of fluid in the pipe shown in that graphics. And if you have a good distribution with the longest pipe, you have the best stratification in the storage tank. There are other methods to slow down the speed. You could use simple horizontal spray tubes. Spray tubes are used in storage technology to reduce the kinetic energy of direct charging. But those spray tubes have also disadvantages. There is a dilemma with this horizontal spray tubes. If you have small holes that allow evenly outlet on the whole length of the spray tube, you have high local fluid velocity, and that leads to turbulence and mixing. So I would not recommend that. You can do bigger holes to have a bigger overall surface where the water can enter to the storage tank. But that leads to the exit of the fluid only at the end of the pipe, where the distance to the storage wall is short again, and that has also again high speed on the end of the pipe and turbulence and mixing. So I couldn't recommend that either. So spray tubes are not a good solution, and maybe you should already forget about that solution and not use it. The next method to bring water in or out of a tank are elbowed tubes and perforated plates in a storage tank. That is used for industrial cases most, where you have only one thermal zone and not several thermal zones. The elbowed tubes guide the fluid into the cover or bottom of the curvature, meaning if you have charging with hot water, it's going up here. And if you use a cold storage, you charge it with cold water, it's going in here to the bottom. It acts as a flow distributor, often used in combination with perforated sheets, meaning a sheet would be placed here in the storage tank and up here with a small hole for the elbowed tube. And the combination is very effectively results in a very good stratification. There are no general design recommendations, but if you use a perforated sheet, it's nearly almost good, always good. I show an example here, 800-liter tanks with an elbowed tube that is charged. If you have a perforated sheet, you keep the upper part hot and charge it and raise the temperature in the lower part step by step until you have a fully charged storage tank. If you have no perforated sheet, the temperature drops in the top region of the storage tank, and you have a mixing processes that are higher with higher speed or higher power of the charging. You see here again CFD simulations with this case I showed before. Only after 4 minutes you have a very big region where you have a mixing without a perforated sheet. And if you use a perforated sheet, you keep the hot water hot and the cold water cold, which is the goal. And here you see the streamlines of the fluid. You have the perforated sheet somewhere here, and the streamlines are very evenly distributed, having a piston flow in the whole storage tank, meaning you push the hot water down to the bottom of the part without destroying the thermocline between hot and cold. And there is a different part for bringing in and out water, that's so-called charging cups. They are used in very big storage tanks or in basins that allows the fluid, if you have a baffle plate, to get out on the diameter of that baffle plate, and that is a very good means to slow down the velocity and have keep your stratification good. So the general recommendations are for the construction are a speed below 0.1 meter per second. That is crucial, and a length of at least 6 times the hydraulic cross section of the pipe to allow the fluid to calm down. And another recommendation is the position of sensors. They should always be in a distance that is big enough to the cold part, that the sensor is not disturbed by the charging process. So now I come back to the check questions. I'm not sure if I should wait for answers, or I should answer them for myself. I see there is something in the chat.
Perhaps you could just discuss the answers already, and
Okay.
perhaps that would also trigger more questions or discussions, Robert, if you don't mind.
Yeah. So, what physical properties of water make it a good choice for energy storage? We talked about the capacity, both the specific capacity and the fuse energy for phase change, and we talked about the density of the water, and that's the main parts: the high capacity of water and the ability to have a stratified storage tank, which is due to the fact that water is the density is dependent on the temperature of the water. The second question was, what is the biggest problem when combining heat pumps with water storage tank, and how is it solved? So the biggest problem is the flow rate of heat pumps. Heat pumps work with small delta T and high flow rates, and the means to overcome that problems is to have a speed below 0.1 meter per second and a calming section inside the storage tank for charging the storage tank. And the third question was, what has a greater influence on the performance of the overall system, the energy losses or the exergy losses of water storage tanks? We did not talk much about the energy losses, but we talked a lot about the exergy losses. But of course, you also lose energy towards the ambient. If you have a storage tank that's 60 degrees and you have a surrounding of 30 degrees Celsius, you lose energy to the ambient. That energy losses are typically in a range of something like 1 kilowatt hour per day in a small tank for domestic hot water for a single family home. If you have a bad stratification but a good insulation, you end up with a performance factor of only 1.6 of a heat pump, and if you have to cover 10 kilowatt hours energy for domestic hot water, you need 6.3 kilowatt hours of electric energy, and you have 1 kilowatt hour of losses, and to overcome those losses you have 0.2 kilowatt hours, meaning in total 6.4. If you have good stratification, you have a high COP. To cover the same amount of energy, you only use 3.4 kilowatt hours of electric energy. You have higher losses, and in combination with the energy that is needed for the higher losses, you have an energy demand of 4 kilowatt hours. So the answer is the exergy losses are important, but of course the best system would be low exergy losses and also low energy losses. And so I come to the end of my presentation. I would like to say many thanks for your attention. I hope the translation into Indonesian language is correct for saying thank you. And now I'm open for question and discussion. And I would be glad if I could answer some more questions. Thank you.
Thank you very much, Robert, for the very interesting and insightful presentation. I think we have a few questions in the chat box, and our team is selecting the questions to be discussed in this session. But before we go into that, perhaps I would like to start with perhaps a question of understanding from my part. We talked extensively about stratification and optimization of stratification. It seems that from your description, to optimize stratification, it doesn't seem like it would need a lot of investment. So could you just perhaps clarify that a little bit? Is a lot of investment needed for that? And then the second question is, you know how Indonesia is a tropical country and a lot of the cities are very hot. So do you think that the thermal energy storage, it could be used to address the cooling challenges for our hot climate? For example, I saw that in your earlier slides, you talked about the concept of district cooling. And perhaps you could talk a little bit more about that, whether that's possible for Indonesia. In Denmark, I know that they have district heating. So is district cooling possible to be implemented in a city like Jakarta, for example? So maybe we start with those two questions, and then I will then raise a few questions from the audience. Thank you.
Yeah, thanks for your idea. I think it's a very good idea to have a district cooling. I never thought about it, I must admit. But your first question was the investment for having a good stratification. You're right. It's not rocket sciences. You don't need expensive measures. It's a cheap solution. You can have same material and same tank, but if you have a clever metal sheet on the right position of the storage tank, it makes a huge difference, and that means keeping the stratification efficiency high is key. It's not expensive. You can do it with low-cost materials and with easy measures, and improve the energy efficiency of your whole system. That's the first part. The second part is, as you said correctly, cooling demand is high in Indonesia. And to overcome the cooling demand, in my opinion, storage is also a very good solution. And there are two possible ways. It's the sensible heat storages. If you have like chilled sailings, for example, they work with a temperature of something like 15 to 20 degrees Celsius as flow temperature. That's a temperature range that could be very good stored in a tank. Lower temperature could be provided by ice, and that if you have a chiller and you produce ice with that chiller, you could use the sun or PV electricity during the day, and cool down a tank or produce ice and use that over the night to have a longer period of cooling with renewable energies, and that could be a solution for cooling demand. But don't forget about the heat, because the industry uses the biggest share of energy, and the industry always needs heat for different applications. It's not only having a cool environment for us, but production of different products often need heat, and the heat is in different temperature ranges. And often you have a process that needs a high temperature, and you have an exhaust gas that is still hot with like 800 degrees, something like that. You could recover that heat. And if you don't have a correct application to use it at that time, you could store it for later use. So heat storage in industry with pressurized steel tanks in a range up to 200 degrees Celsius is also an important part where you can use thermal energy storages. And towards the smart systems and smart energy, here is the point that you have times with an excess of power or excess of electricity. Maybe you have a sunny day and a lot of PV, and with smart storage tanks, where you have a good stratification, you can produce heat out of the excess PV electricity and can store that heat for later use. And the last question was the district cooling with a big storage tank for district cooling. In Switzerland lately, so-called energy nets, grids are a topic where everyone can put in heat in or out as a source of a heat pump or as a sink for cooling demands or things like that. But that would mean you have the possibility to get rid of excess heat when you produce cold with a chiller with that energy net grid. That could be a solution. If you have a centralized cold tank to distribute the cold, why not? I think it's a nice idea. I don't see now any points that speak against it.
Thanks, Robert. Just a question, off the top of my head, because we have a lot of large offices and some are quite centralized also. Just a thought whether that's a possibility. But you also raised a very important point that the industry uses the majority of the heating, for example, right now, including in Indonesia. So thermal energy storage for heating is also a very important point that can be optimized and utilized by the industry. So I will now raise a few questions from the audience. We have very interesting ones. The first one is from Andi Ramdhani, and his question is, how can thermal energy storage be integrated seamlessly with the existing infrastructures in Indonesia right now, which is dominated by coal-fired power plants? Are there any technical or logistical challenges in doing so, especially if you want to connect it to the smart grid? I think you also mentioned about it briefly. And also, if the system is decentralized, is it also possible? So perhaps we answer that question first before we go to the next one.
Okay, I try to. So as I understand the coal-fired part, is also used to generate electricity.
Yes.
And if you use a coal-fired power plant, you use also water. You use steam, but not for storing energy, but you generate steam and run a turbine with that steam. That's not a storage. And here I don't see the possibility of electricity production in coal power plants. Maybe you can reduce the energy demand on other point of your system in order to get rid of that coal power plants. But in that power plants, I don't see where the thermal energy storages could fit in for electricity production. I'm sorry.
Okay, good. And the second part of the question was about linking thermal energy storage with smart grids. Technical or logistical challenges in doing so, or is it easy to do it?
You have to know the state of energy of your storages. Meaning you have to know, is there some capacity left to heat it, and you have to have a management of your energies. Meaning, if you have excess heat somewhere, you can also only store it when you managed your storage tank before that to be let's say empty. It shouldn't be empty. If you have a good stratification, you can let the average temperature drop to a quite high degree, serving the needs still with the upper part of the tank that is high, but you need to have a bigger dimensioning of your storage tank to take that heat and store it there. But it could be the transition of excess electricity to thermal power, and then you can store it in a tank. When you need the state of energy of the storage, you know the state of energy of storage tank, and you allowed the tank before to cool down low enough to be able to store that heat.
Okay, thank you, Robert. Moving on to the next question. This seems like a pretty straightforward one. What kind of specifications of the water is needed for thermal energy storage? For example, does it have to be like pure water, or is it water that has a lot of minerals or electrolytes? Because water is corrosive also. So what kind of maintenance is required as well for the storage tank?
Yeah, so it depends if you have an open system or a closed system. Most systems are closed systems, and you don't have any special needs for your water. You can only use normal mains water and put it in.
Sorry, can you remind us again what closed and open water systems are? Just as a reminder.
A closed system is a system where the water is not exchanged. You fill in water if you take a system into operation,
okay,
and then you won't change that water. You can fill in then normal water from the mains that has some gas inserted, oxygen, and that's corrosive. That's correct. If you have a normal black steel storage tank, some corrosion will occur. That's for sure. but only as long as there is still gas in the water, and that gas is sometimes just used, and then it's we call it dead water because there is no gas inside the water, and the corrosion will stop. That means in a closed system, you have no special treatment of the water necessary. You should take care if you have some maintenance or something like that. It's a good idea to capture the water of your plant and bring it then after your maintenance back into your system. But nothing special is needed. If you have an open system where fresh water is entering from time to time, then you don't treat the water. You usually use stainless steel to prevent the corrosion in the system. So closed systems, only water, using black steel, allowing corrosion, but it will stop when the gas is gone. And open system, use stainless steel in order to prevent corrosion.
Okay, thank you. Our next question comes from Samuel Bima. What are the most effective materials for thermal energy storage in terms of energy density and thermal conductivity? And how do these materials perform under varying operational temperatures?
I showed a slide with different materials.
Right, yeah.
Part of it is already mentioned. Maybe the question was before I showed that slide.
Yeah.
But water has a very high capacity, but it's limited in temperature. Meaning water is very good in a region up to 180 degrees, maybe 200 degrees if it's a pressurized system. Above that, it's not a good solution. If you have big solar power plants that produce electricity out of solar heat, you usually want to operate that systems 24 hours a day, but you have sun only 8 or 9 hours, and then you need storing high temperatures to produce steam later on. And that high temperatures could be stored in molten salt. That's a common solution for that. The disadvantage of molten salt is that you have to keep it hot all the time. It should not crystallize. So if you have a few days without sun or a problem in your power plant, you have to put in electric energy to keep the molten salt hot in order not to lose your storage system. So molten salt is a system that could also be used for higher temperatures. What I have in mind is also storages that's lately common with molten aluminium. But I'm not an expert on that. I can't talk about the physical properties. It's harder to integrate because it does not have the advantage of water that it's compatible with your rest of the system. If you have water or steam, your that's technology that is commonly spread. If you have other materials, you need some measures to put in or exchange heat to a water or steam-based part.
Right.
I hope I answered it. Maybe again, one more physical property is the energy of use. so the phase change at 0 degree for ice is also in favor of water for cooling applications.
Yeah. It's interesting that you also mentioned molten salt to increase the performance, because one of the participants also asked whether molten salt is required for distributing the heat for generating the heat in the water. And I think you already answered that question.
Okay.
Okay. Moving on. Go on.
I just thought about thermal oil is also a material that is used also in combination with solar power plants. But for higher temperatures, this oil is also a method to transport heat, but not to store heat.
Okay. Okay, the next question is from Hanif Yusran Makarim. He said that you previously mentioned about the length of the tube or the pipe that could be influential for energy efficiency storage. So his question is, in Indonesia, thermal energy is usually stored in places that have tricky contour, or that the country's topographical aspects is not always flat. So will that be influential for energy storage or the tube or pipe installation? And if it does, do you have any suggestions for how to handle that issue? So the topography of Indonesia that is not always flat, because we have lots of mountains and yeah.
Well, I don't see a problem with that. So the length of the pipe was meant inside the volume of the storage tank.
Okay.
If you have an entrance to a storage tank, and then you have a change in direction of the water entering the tank, you have an additional pipe to calm down the flow in that section to enter the storage tank in a good way. But we're talking about 40 centimeters for domestic applications, or maybe a meter in an industrial scale. That's not related to topography of the country. What could have an influence is the shape of your tank. I showed pictures of those big steel tanks, pressurized or non-pressurized for industries. They usually tall and slim. And I mentioned that to reduce the negative effects of conductivity of the material for stratification, that tall and slim storage tanks should be used.
Yeah.
But the effect of conductivity is a slow one. So that is necessary if you have storage of heat over longer periods of time. If you have a charging process per day, it doesn't matter. You can have a tank fitted in your topography as it is possible. You don't have to have those high and slim storage tanks. You can only have a cubic volume or something that you could build in the countryside.
Thanks, Robert. The next question is from Firdaus Ilham. Is it possible to capture direct solar thermal energy into the thermal energy storage system without converting it into electricity first?
Yes, it is. I know in different countries in Africa, a typical solution is to have a black tank on the rooftop that collects sun. So the tank itself is kind of a collector. You have a painting on the wall, and it will heat up. But the efficiency is low, or you capture not much energy. But solar thermal heat is a very good solution. Solar collector with an absorber made of a metal sheet coated with an coating that collects heat, covered with glass to prevent heat losses, produces heat directly of the sunlight with a high efficiency, and you can connect that to your storage tank. You don't have to have an heat exchanger. You can have the same liquid in the storage tank and in your collector. And here in Switzerland, it's usually with antifreeze additives to the water. That's not necessary in Indonesia. Yeah. You can use pure water without heat exchanger, a solar thermal collector, produce heat and store it in a tank without any other, without the way over electricity.
Yeah. Speaking of application in Switzerland, are there any incentives from the government for the use of thermal energy storage that you know of? In Indonesia, renewable energy and renewable energy supporting technologies are still relatively new, and often to introduce such technology, there are incentives provided by the government to increase its uptake. And I was wondering whether how the situation is in Switzerland regarding thermal energy storage.
The thermal energy storage is treated as a part of the whole system. They don't have incentives on the tank alone. Mm-hmm. But if you want to use renewable energy with a heat pump, so ambient air as a source for your heat pump, and electricity maybe from PV, and store that heat, you have to have something. It's called system module. You have to have a system that is like certified, including the storage tank. And if you set a special thing here, we have heating demand, and we have domestic hot water demand. And we store both often in one device, a tank that has 60 degrees on top, 30 to 35 in the middle for heating systems, and cold area in the bottom. And that storage tank has to fulfill some requirements on the stratification efficiency. And if that storage tank is certified, you can have subsidies for your whole system to get money from government to use it.
Right. So no specific incentive as such, but if you integrate it or use it with renewable energy technologies, then you're able to apply for a subsidy or something like that. Is that correct?
So indirectly, yes, but not directly. So it's part of the system.
Yeah.
There was for solar thermal energy subsidies. And here there was a rule that you had to have 20 liters of storage per square meter of collector area. Mm-hmm. And then you get subsidies, but it's indirectly, not directly storage tank.
So is it correct to assume that most of the usage in Switzerland right now is for industrial usage rather than for personal or residential purposes? Would you say that?
In Switzerland, every house has a storage tank. So it's a common technology for both residential area and industrial area. And we also have lots of district heatings. You mentioned Denmark before. In Switzerland, they are not as big as in Denmark, but the number is growing. And so some district heating systems always have a big storage tank.
Right.
And in industry, it's a shift of usage of heat, and the heat pump, high temperature heat pumps, the usage of high temperature heat pumps is rising. And here the storage tank is more and more important. But most of the tanks are used in residential buildings, district heatings, and parts in the industry for food industry or something like that. There is storage also important.
Right. Interesting. Okay, moving on to the next question. This is from Jerry Aluansius. His question is, do you know how thermal energy storage can be integrated with other peak demand management strategies to improve grid stability? Is that clear enough as a question?
Yes.
Whether it can be used?
It's clear enough.
Yeah.
I can. I just again have to talk about the situation here, where I know it, in Switzerland and also in Germany. There is a label called the Smart Grid Ready label that is available for heat pumps, for generating of heat. And that label means that you have a communication of your grid operator to the heat pumps, with 2 contacts giving 4 operating states. And that operating states for the heat pump are regular operation, forced operation, or it should use electric energy, or it is not allowed at all to use energy, so again, I start from scratch. So no operation, stop. Normal operation, you should use if possible, or you have to use the heat pumps. That's the 4 operating states that are communicated. And here the storage is crucial, because if your storage tank is full, when your grid operator says run your heat pump to make heat out of electricity, then you are not able to, and you can't fulfill it. So here the management of the thermal energy content of the storage tank is important. The same is for the operation saying stop operation. But you have a demand in your building for heating or maybe for domestic hot water. That means your storage tank has to be in a state of charge that allows, on the one hand, to operate your heat demand from the tank, and on the other hand, there is enough capacity left to run the heat pump if there is no demand. And that's a measure of providing grid stability. Your grid operator can shift load in the residential buildings and say, do operate because the grid needs it, or do not operate because the grid is overloaded. And that, therefore, the storage tanks are an important part.
There's a related question, I think, with the previous question. I wonder whether you could also answer it. This is from E. Najib. Can water-based thermal energy storage optimize the existing coal-powered infrastructure by storing excess energy during off-peak hours and using it during peak demand? I think you mentioned that it's not possible to use thermal energy storage in coal-fired power plants, but in this situation, is that possible? So using thermal energy storage to store excess energy during off-peak hours and then just using it during peak demand.
Yeah, so that is, again, coal power plants provide, like we call it, band energy, so it's energy that is provided very straight, so not switching on and off all the time, but you want to provide it on a reliable way. And if you have renewable energies that's fluctuating, you could switch off a coal-fired power plant. And here, if you have the storage, you can even out the fluctuating renewable energies and maybe stop operating of the coal-fired power plant. And I don't know if that is it's enough as the answer, but it's the evening out of the fluctuating renewable energies with storages that could prevent coal-fired power plant to operate.
Yeah, in Java, for example, we have an oversupply of energy or electricity generation in the main Java Bali grid, and so I think this is where this question is coming from, because there is an oversupply. Okay, moving on to the next question from Hairunisa. How can advanced control algorithms and predictive maintenance techniques be integrated into thermal energy storage systems to enhance efficiency and reliability of heat pumps in a smart grid environment? Do you know of any case studies, for example, or do you think it's a good idea to integrate advanced control algorithms and predictive maintenance techniques?
Yes. In the weather forecast could be used. Here, it could be used to forecast heating demand. In Indonesia, it could be used for cooling demand. And that means you have maybe information about your status of the grid, how much power is available, and if you could use it, or maybe different tariffs for electricity. And with a weather forecast, you could predict if you need a lot of cooling on the next day or not. And then you could use that for operating your system. If you have a storage for cooling power, you could optimize your system very good with those predictive control of energy systems.
Okay.
And again, storage tank is an important part, because you have to store the excess heat, or take into account how much storage you have left for your demand. And you could use an ice storage to produce ice, and use it then on a period without a lot of renewable energy.
Right. Thanks, Robert. The next question from Farah Ramadhani. Hi, Robert. What do you think of using two types of fluid at the same heat storage? For example, oil for high temperature and water for low temperature. Does that make sense? And will it change each other, or would it work like in stratification? Or is it sort of like stratification too? Sorry, I hope that's clear enough.
That means separated volumes with in different temperatures.
Right.
The challenge here is that you have to have a heat transfer between the volumes and heat exchanger that is preventing or providing heat or extracting heat from your storage tank. You're right, with oil you could have a higher temperature, but it's very difficult to treat because of the its poisonous, and it's you have to have different ceilings, and you have to have safety measures to overcome those problems. That's one thing preventing it, because if you have different fluids, your system gets complicated and expensive, and you have to have new elements in your systems that has to work correctly. And the other thing is, as I mentioned, the heat exchanger. But what I see could be done is a combination of phase change and materials and water. That's a solution that is already done. You can have some encapsulated phase change materials swimming in a water basin that take up heat if necessary, and give it back if you have the water below the melting point of your materials. There you have different materials but not different fluids. And the phase change material has to be encapsulated, which means it's kind of an heat exchanger, and you have the heat transport through the wall of your encapsulated material.
Yeah. Okay. I think we have perhaps time for just 2 more questions. So the next one is again another question from Andi Ramdhani. Are there any fundamental limitations in terms of energy charging and discharging speeds in thermal storage systems that affect their application in dynamic grid systems? And given the cost of thermal energy storage technology is often high at the outset, I'm not sure whether that's correct, because I think you already mentioned that it's not too expensive. Is there already a widespread adoption of this technology in the broader energy market, or is there a delay, do you think?
So that's one of the big advantages of water, because if you operate your whole system with water, you don't have to rely on heat exchangers that slow down the heat exchange. But you can directly put out the water and use it and put in cool to your tank. So the power that is applied for charging or discharging of your tank is nearly limitless. That's a very, very good situation with water. And the cost of storage tanks often you have to have a storage tank anyway. Extra cost is then needed when you want to dimension a tank with a higher capacity to have the possibility to use excess heat or to collect energy in times where the energy is available. That raises the cost of storage. but the numbers have to be calculated in each case again. So it's not a common calculation of that.
Okay. Okay, thanks, Robert. I think this is our last question. Let's see whether we have time for two more or just one more. The next question is from Abdi Putra. What are the key factors to consider when optimizing these systems, thermal energy storage systems, for residential use? Are there any special considerations for residential use? And do you have any suggestions on how to optimize the implementation of heat pumps, thermal energy storage systems in Indonesia?
So I'm sorry that I always have to come back to the situations that I know here.
Sure.
Because here we have a heating demand for space heating, and that heating demand for space heating is usually covered by heat pumps. That's nowadays the normal way of producing heat. That means we have a heat pump anyways. And if there is a heat pump available in a residential building, it's most cost effective to use it also for domestic hot water preparation, to heating up water. That means the investment cost of the heat pump is needed to cover the demand of space heating, and then it's also used for domestic hot water in one device. Even if there is a discussion about direct electric domestic hot water preparation, that's also possible. But in Switzerland, it's forbidden. You are not allowed to directly heat up water. In Indonesia, the situation is different, because the heat pump is not always there. It's a new technology. And I guess a simple heating rod in a tank is very often used for domestic hot water preparation. Please correct me if I'm wrong. And if you want to replace that heating rod, you have a high investment cost for the heat pump. Except you use a heat pump that is combined with a storage tank, which is a technology that is available, so-called in German Wärmepumpenboiler. It's a tank with the refrigerant part of the heat pump integrated into the storage tank, using air as source of the heat pump and giving the energy directly to the water. And that's very energy efficient, because you have a good source of your heat pump. You don't have to have a device with a high power, because you have a storage tank, and you can take 4, 5, 6 hours per day of domestic hot water preparation when the sun is providing PV electricity, and then you can store it in a storage tank for use on a later time. So this combination of domestic hot water preparation with heat pumps in one device combined with a storage tank is a cost-effective way and an easy way.
Okay, thanks a lot, Robert. Perhaps we have, I don't know whether this can be answered very quickly. Maybe just one more. Given Indonesia's abundant geothermal resources, can thermal energy storage, the technology, can it be integrated with geothermal power plants to ensure a stable and continuous supply of electricity, even during the fluctuations in geothermal activity or energy demand? Would you happen to know how to answer that.
So the geothermal power generation means electricity from geothermal sources.
Right. Yes. Yeah.
I'm sorry, I'm the wrong person to answer that question.
No problem. I think the New Zealanders probably would have a better idea because they're the experts. Right. Okay. Well, thank you so much, Robert, for the very interesting and insightful presentation and discussion. Unfortunately, that's all the time we have for the question and answer session. For all participants, I hope that we answered your questions sufficiently, even though there are still a few questions in the chat box. You might want to see, Robert, what other questions were given to you in the chat box. There are a total of 30 questions, so quite a lot. Thank you very much, everyone, for your participation. And let's give a big applause for Robert and for putting so much of his time to preparing the presentation and also for the Q&A session. So thanks again, Robert. And now, Sobat Energi, karena waktu yang terbatas, kita telah sampai di penghujung acara. Izinkan saya mungkin merangkum beberapa poin dari presentasi Pak Robert. Yang pertama, Pak Robert membahas pentingnya penyimpanan energi termal untuk menyeimbangkan permintaan dan pasokan energi, untuk meningkatkan efisiensi energi, dan juga dapat diintegrasikan dengan sumber energi terbarukan. Beliau juga menekankan bahwa air adalah media yang paling efisien untuk menyimpan panas, karena kapasitas panas yang bisa mencapai suhu yang sangat tinggi, ketersediaannya, faktor keamanan, dan juga kompatibilitasnya dengan infrastruktur yang ada. Beliau juga menjelaskan konsep stratifikasi penyimpanan, yaitu pelapisan alami air pada suhu yang berbeda di dalam tangki penyimpanan. Dan mempertahankan stratifikasi itu sangat baik dan sangat penting untuk memaksimalkan volume tangki penyimpanan yang dapat digunakan dan dapat meningkatkan efisiensi pompa panas. Dan dalam presentasi beliau disampaikan pula 3 proses yang dapat mengganggu stratifikasi, yaitu konduksi panas, arus entrainment, dan aliran masuk turbulen. Selain itu, Pak Robert juga memberikan rekomendasi untuk desain tangki penyimpanan dan konstruksi diffuser untuk meminimalkan gangguan-gangguan tersebut. Demikian Bapak Ibu, webinar PPSDM KIBTKE dengan tema Optimizing Thermal Energy Storage for Smart Systems and Heat Pumps. Dari panitia telah memilih 2 penanya terbaik pada siang hari ini. Selamat kepada, siapa ya kira-kira? Oke, selamat kepada Bapak Andi Ramdhani dan kepada Ibu Farah Ramadhani. Sebagai 2 penanya terbaik kita dari panitia akan menghubungi pemenang untuk mendapatkan hadiahnya, dan panitia akan menghubungi via WhatsApp atau telepon yang dipakai ketika melakukan registrasi. Adapun sertifikat bagi peserta akan disediakan dalam 2-3 hari ke depan. Pastikan Bapak Ibu ya mengisi formulir evaluasi di link yang tertulis di chat box. Jadi jangan lupa untuk mengisi formulir evaluasi. Dan Sobat Energi, di penghujung acara ini sepertinya nggak lengkap ya kalau nggak ada pantun. Jadi izinkan saya menyampaikan pantun. Air mengalir jernih bercahaya, energi tersimpan tak terbuang sia-sia. Mari bersama menjaga bumi tercinta dengan teknologi yang ramah dan berdaya. Terima kasih kepada Pak Kepala PPSDM KIBTKE yang sudah hadir sampai selesainya acara kita. Dan narasumber kita, Robert, thank you very much once again. Dan kepada seluruh peserta webinar yang sudah aktif dan semangat mengikuti acara. Semoga materi yang disampaikan ini bermanfaat dan menambah pengetahuan, serta tidak lupa kami memohon maaf apabila ada kekurangan dalam penyelenggaraan. Dan jangan lupa untuk follow Instagram PPSDM KIBTKE untuk informasi webinar dan kegiatan-kegiatan selanjutnya. Terima kasih. Wassalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam.
Terima kasih Pak Edi.
Thank you Pak Robert. Terima
Thank you very
kasih
much
Bu
again
Dian.
for letting me talk.
Terima kasih. Thank you. Thank you. Terima kasih Bu Elin, Pak
Terima
Zainul.
kasih Bu Dian, Pak Robert.
Dunia terus berubah dan juga beriringan dengan semua kebutuhan di dalamnya. Di dalam kehidupan manusia sehari-hari, sumber energi menjadikan hal yang utama bagi keberlangsungan hidup manusia hingga diperlukannya sumber energi terbarukan. PPSDM KEBTKE hadir untuk memenuhi semua tantangan-tantangan yang ada di masa sekarang ini. Di bidang ketenaga listrikan, energi baru dan terbarukan, serta konservasinya agar bidang KEBTKE dapat dikelola secara baik. Mengelola sumber daya manusia di bidang ketenaga listrikan, energi baru terbarukan menjadi fokus utama bagi PPSDM
Thanks, Robert. Have a good day.
untuk menjadikannya SDM yang berkompeten, profesional, berdaya saing, dan juga bermoral dalam lingkungan global di bidang ketenaga listrikan atau energi baru terbarukan dan konservasi energi. Dengan program-program unggulan yang diterapkan PPSDM KEBTKE dan juga didukung oleh para pegawai yang profesional dan berdedikasi tinggi. Demi melengkapi kesempurnaan pembentukan sumber daya manusia di bidang ketenaga listrikan, energi baru dan terbarukan. Demi menciptakan dan membentuk SDM yang kompeten, profesional, dan berdaya saing tinggi. PPSDM KEBTKE memfasilitasi seluruh peserta didik dengan sarana dan prasarana yang sudah memiliki standar ISO. Laboratorium dan workshop menjadi fokus sarana dan prasarana di wilayah Pusdikat KEBTKE.
PPSDM KEBTKE, Kementerian Energi dan Sumber Daya Mineral, telah bertransformasi menjadi sebuah lembaga pengembangan SDM di bidang ketenaga listrikan dan EBTKE yang unggul dan selalu menjaga kualitas layanannya. PPSDM KEBTKE mendukung target nasional Net Zero Emission 2060 melalui transisi energi yang harus diwujudkan oleh semua pihak untuk mengurangi dampak perubahan iklim bagi kehidupan masyarakat. Selain itu, Indonesia memiliki energi baru terbarukan dengan potensi yang tinggi, mulai dari matahari, hidro atau air, angin, bioenergi, panas bumi, serta lautan. Hal inilah yang membuat kami semakin matang dan siap melayani Anda. Kami didukung oleh para fasilitator yang berkompeten dan fasilitas yang lengkap sesuai dengan kebutuhan pelatihan, sertifikasi, bimbingan teknis, dan layanan penunjang lainnya. Pelatihan dan sertifikasi dilaksanakan dengan layanan yang prima. Bergabunglah bersama PPSDM KEBTKE.
Program diklat di dalamnya dibagi menjadi 4 kelompok besar, yaitu bidang ketenaga listrikan, energi baru terbarukan, konservasi energi, serta manajemen. Bidang ketenaga listrikan terdapat beberapa diklat unggulan yang mencakup diklat teknis inspektur ketenaga listrikan, diklat teknis perencanaan ketenaga listrikan, diklat teknis perizinan ketenaga listrikan, diklat teknis uji layak instalasi listrik, diklat teknis perhitungan tarif listrik, diklat teknis pengembangan listrik perdesaan, diklat teknis pengelolaan dan pemantauan lingkungan bidang ketenaga listrikan, dan diklat teknis pengelolaan PLTMH. Di bidang energi baru terbarukan, dikembangkan beberapa diklat teknis, di antaranya diklat teknis pengelolaan PLTS, diklat teknis pengelolaan PLTB, diklat teknis pengelolaan biogas, serta diklat teknis lelang wilayah kerja pertambangan panas bumi. Sementara untuk bidang konservasi energi, diikuti diklat teknis kiat-kiat konservasi energi, diklat teknis audit energi, diklat teknis manajer energi, diklat teknis penghematan energi dan air, diklat teknis adaptasi dan mitigasi gas rumah kaca, dan diklat teknis perencanaan energi. Dengan itu semua, saat ini PPSDM KE-BTKE mempersiapkan sebuah wilayah yang akan dijadikan sebuah kampus besar diklat tersendiri di daerah Cisarua, Jawa Barat, yang akan didirikannya sebuah fasilitas lengkap untuk memenuhi kebutuhan para pengajar dan peserta didik. Kampus Desa Kuta dan Kampus Desa Cisarua merupakan sebuah bentuk keseriusan PPSDM KE-BTKE untuk terus menciptakan sumber daya manusia yang berkompeten, profesional, dan berdaya saing tinggi di setiap bidangnya.
Baik. Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Hari ini saya mengunjungi beberapa fasilitas PPSDM, khususnya yang ada di Satker PPSDM KE-BTKE yang berada di Cisarua dan di Megamendung. Kita melihat nih di belakang kita, ini beberapa fasilitas yang harusnya nanti muncul di sini, beberapa pelatihan-pelatihan yang kita bisa manfaatkan berdasarkan lokasi yang ada di sekitar sini. Jadi kita berharap kita semuanya bisa memanfaatkan, terutama terkait dengan pelayanan untuk masyarakat. Saya sangat mendukung pengembangan PPSDM KE-BTKE untuk memanfaatkan aset-aset yang ada guna perkembangan institusi ini supaya lebih maju lagi ke depannya. Terima kasih. Jaya selalu PPSDM KE-BTKE.
Pengembangan sumber daya manusia adalah proses pelatihan pengetahuan dan sertifikasi sumber daya manusia. Maka dari itu, PPSDM KE-BTKE hadir dalam sebuah lembaga yang memfasilitasi sumber daya manusia yang baru. Kami siap menciptakan sumber daya manusia yang cepat, cermat, dan produktif.